Hi, here we are going to see about the today Unit 5 continuation part. So let me see the one by one. So instruction level parallelism. So in instruction level parallelism, we are going to see about the VLIW architecture. So the each instruction is specific parallelism that should be taken several operations to be done in parallel. So this very long instructions and word processing will increase the number of instructions that processed per cycle. So it is essentially a concentration of several short instructions, and it requires multiple execution units. So running in parallel to carry out the instructions in single cycle. So it will execute multiple instructions of cycle and use simple regular instruction set at the same time. So the VLIW processor will combine many simple instructions into single long instruction word that will be uses the different registers. So the language compiler or preprocessor that will separates the program instructions into basic operations that are performed by the processor in parallel. So these operations are placed in very long instructions word. So the advantages is it should be having increased performances, better compiler targets, simple hardware compilers, and it can spot ILP easily. Disadvantages means there is a little compatibility between the generations, increased memory use, high power consumptions, explicit NOPs, block code sizes, misleading MIPs ratings. Next, scalar architectures. So that is the hardware which is responsible for finding the ILP instruction LP learning processing, that is in sequential programs. So in this superscalar architecture, the advantages is it is very compatibility between the generations of one generation to another generations, and the disadvantages it is very complex, and this hardware will be complex to use in other memory processors or anything else. Next, explicitly parallel instruction computing, that is we shortly known as EPIC. So it is a combination of a VLIW and a superscalar architecture, that is the very long instructions, long instruction word architecture, as well as the scalar architectures. Both these architecture together combine to forms the explicitly parallel instruction computing. So these instructions are grouped into 3 operating blocks and template block. So this template block will tell hardware if the instructions can be executed in parallel or series. So likewise it will be tells the hardware instructions. Also it will gives the information whether the blocks can be executed in the parallel form or in the series form. So this makes the instruction computing very easy for the architecture to process the method. Next, ILP versus power. So increasing the instructions per cycle, it will requires the fewer cycles to execute the task. So it uses sorry, it uses a longer clock for same performances, and also it uses a lower supply voltage, hence it uses the less power for the voltage level. So however, too many functional units and too many transitions per clock will cycle will increases the power consumptions that should be occurs in the increasing instructions or cycles. Next, low power architecture. So that is the power consumed by the additional circuits versus the ability to lower the clock rate while maintaining the performances. Next thing, the circuits must be highly used. It should be move complexity into software processor. The voltage scaling that will be reduce the VDD level. So that is the voltage output, voltage value. Clock grating means there is a churn of the clock when a chip is not in use. So it applies to the submodules of a chip also. So that makes the low power architecture more processing and increase the number of instructions that should be processed per cycle. VLIW is more suitable than the superscalar for the low power processing. It is also smaller for the same number of functional units, and it will compile better at the finding parallelism than the hardware processing. So it also put the multiple processors on a chip rather than lots of functional units in one processor. So it also helps in running independent task. So these things will be makes the VLIW more comfortable, and that operations will be placed in a processor can disassemble and transfer each operations to the appropriate execution unit. Next, improvement of speed by pipelining. So that is, the processor speed can be enhanced by having the separate hardware units for the different functional blocks. So with the different buffers between the successive units. So it is also having the number of unit operations into the instruction cycle of processor, and it can be divided for the purposes that will define the number of stages in pipeline. So the processor which will having a n stage pipeline would have up to n instructions. Simultaneously it should be processed by the different functional units of processor. So the effective processor speed will increase ideally by the factor which is equal to the number of pipelining stages. So there are 4 pipelining stages. So the clock cycles have been mentioned at the top. So this pipelining will be having the clock cycles as well as the instructions that should be maintained in the processing units. So this instructions execution will be divided into 4 steps. So that is the processor I1, instruction set 1, instruction set 2, instruction set 3, instruction set 4, and the instruction set 4 instruction sets have been mentioned there. So this should be maintained, that is the D1, F1, D1, O1, W1. Likewise for instruction set 2, F2, D2, O2, W2. Next F3, D3, O3, W3. Next one is F4, D4, O4, W4. Here storage buffers are divided into the hardware organization as a fetch. F means fetch instruction. So first we have to fetch the data and then transfer it to the B1 value. Next second thing will be the decode instruction and fetch operands. So after fetching the instruction set, it should be decoded to binary to decimal, like that we have to decode the values. Then pass into the B2. After that O means perform operation. Which operation you are going to perform, that operation will be performed. That is, addition means addition, subtraction means subtraction, multiplication or division, anything will be happened. After that pass to the B3, then we have to write the result operations. Data dependency in pipelining. So that is first it starts from the F1, D1, O1, W1. After that one cycle it will be shifted to D1 from the F2, D2, O2, W2 idle. So our next step it will be shifted to next one, that is D2, that is F3, D3, O3, W3. After that it should be shifted to D3, that is the F4, D4, O4, W4. So the bubble will be ends here. So likewise the data dependency will be having the pipelining processor. If the input data for an instructions will be depends on the outcome of the previous instruction, the write cycle of the previous instruction has to be over before the operate cycle of next instruction. So it can start, that is the pipeline effectively idles through one instruction, and it will create the bubble in pipeline that persists for several instructions. Next example of dependency, that is a gives 3 plus a, b gives 4 into a. So it can't perform the two in a parallel form. So another cases a equal to b plus a and b is equal to a minus b and a is equal to a minus b. Swapping without the temporal. So examine how you can handle this examples. Branch dependency in pipelining. So first we have to use the branch instruction. Then after branch instruction is given, we have to use the executed if branch is not taken or not. So next we have to execute for unconditional branches. After that, for conditional branches, if taken, it will be processed in a branch dependency in pipelining method. So branch dependency in pipelining method. So the branch instructions that can cause a pipeline stall if the branch is taken as the next instruction has to be aborted in that case. So if I1 is an unconditional branch instruction, the next fetch cycle F2 can start after D1. But if I1 is a conditional branch instruction, F2 has to wait until O1 for the decision as to whether the branch will be taken or not. Likewise, it will be makes the dependency level. Next, pipelining Dtsp 219X processor. So 6 stages of instruction pipelines are there with a single cycle computational units. So first thing will be the look ahead. That is it places the address of the instruction in going to be executed several cycles down the road on the program memory address bus. Second thing will be the prefetch. Prefetch means that is the instruction if the instruction is already in the instruction cache. Third one will be the fetches, that is fetches the instruction that was look ahead 2 cycles ago. Fourth one will be the address decode, that is decoding of the DAG operand fields in the opcode in this cycle. Fifth one will be the decode, that is the second stage of the instruction decoding process where the rest of the opcode is decoded. And sixth one will be the execute, that is the instruction is executed, status updated, results returned to the destination level. Causes for pipeline stalls. Memory block conflicts if both the instruction and data are to be fetched from the same block of memory. That is, the stall is automatically inserted together. Next, DAG. DAG means that is usage immediately or within the 2 cycles after the initialization. For example, I2 is equal to 0 into 1, 2, 3, 4. A into 0 is equal to dm into I2, M2. So bus conflicts is that instruction which uses the PMA or PMD buses for data transfer may causes the bus conflict. Example, PM into I5, M7 is equal to M3. Avoiding DAG related pipeline stalls. Note that I2 equal to 0 into 1, 2, 3, 4 and I3 equal to 0 into 0001. I1 is equal to 0 into 002. So A into 0 is equal to DM, that is I2, M2 will not causes the stall. So we have to note that switching DAG register banks, that is primary to secondary, will be immediately before using the not cause a stall.